Okay, so after theorem, after that previous remark 3613, we are now going to see proposition 3614. It has a name also, it's called cardinal arithmetic. This result tells us how cardinalities of finite sets are related to the set theoretic operations. So let's see the statement. It has some parts or subdivisions. The first one is this. Let X be a finite set and let small x be an object that is not an element of x. That means small x is lying outside x. Then this union is a finite set and its cardinality equals the cardinality of x plus 1, which seems quite natural. If you bring in something from outside, then the cardinality, the union stays same. What the hell am I saying? Union does not stay same. The union is still finite and its cardinality increases by 1. Okay. Then in B we have two sets. Let X and Y be finite sets. Then their union is finite and its cardinality is related to the cardinalities of x and y by this inequality. It does not exceed the sum of the cardinalities of x and y. If in addition x and y happen to be disjoint, there is no common element, then in place of this inequality we have equality. Then part C. In part C we deal with subsets. Let X be a finite set and Y be a subset of X. Then Y is also finite. And its cardinality does not exceed the cardinality of x. If in addition y is not equal to x, that is, if y happens to be a proper subset of x, then the cardinality of y is strictly less than the cardinality of x. Okay, then D. In D we have functions. We have a function. Let x be a finite set and f from x into y be a function. Note that we are not saying anything about finiteness of y. Y may or may not be finite. We don't need that here. We only know that x is finite and f is a function from x to y. In fact, the only role y will play here is that it's the range of this function. Since f needs a range, so that's why we have a y. Y may very well be infinite. Then the image of x under f, the set of all outputs, is finite and its cardinality is less than or equal to the cardinality of x. If in addition f is 1 to 1, then we have equality here in this inequality. Don't forget that by one-to-one function we mean an injective function, not a one-to-one correspondence. That is a bijective function. And two more are there. E. Let x and y be finite sets. Then their Cartesian product this is finite and its cardinality is equal to the product of the cardinalities of x and y. And finally, part F, this is E. Let x and y be finite sets then this set is finite and its cardinality is equal to this natural number. Okay, now there are you recall that this is the set of all functions where the domain is x and range is y, and we came across this set in the axiom of power set. So there we saw this set. That axiom says that if x and y are two sets, then that collection of functions is itself a set. Okay. Now there are 2 points here, 2 observations. One of them is that looking at these results, you may feel that they are so natural that they are almost obvious. That's because we are so familiar with the natural numbers that these things become obvious. And one other reason for that is that This is the way we have been taught about natural numbers using sets and their cardinalities. From our childhood, we have been taught like this. So that's why these results seem so natural. Nevertheless, since they are results and we have an actual definition for finiteness of sets and what the cardinality of a finite set is, so we have to use that definition, those definitions, to prove these things rigorously. Without proof, we can only guess that they are correct. We will never be sure, so we need a proof. Okay. And the other thing is that you can see this notation, x comes as a superfix of y. The reason for this notation becomes clear from this formula. This notation tells us that the form of this formula will be like this. The form of the cardinality is like this. There is one more thing. Recall that towards the end of our development of the system of natural numbers, actually at the very end, we defined what it means to raise a natural number to a power where the exponent is also a natural number. So this is already defined for us. Okay. Now the proof of this will be, we will handle that in the exercises, because most of the results in tau don't have proofs. Only some very difficult results have proofs, but these are left to the exercises. So there only we will solve it. Instead, we look at a remark which comes after this. So this is remark 3.6.15. Let me just write what Tao has written and then we will try to understand what this means. Proposition 3.6.14 suggests that there is another way to define natural numbers not only natural numbers but arithmetic operations on natural numbers. Not defined recursively using the piano axioms, as in definitions. Two, 1, 2, 3, 1. And 2, 3, 11. But instead using the notions of union, instead using the notions of union, Cartesian product and power set, and this is an alternative foundation. this is the basis of cardinal arithmetic. Which is an alternative foundation to arithmetic than the piano arithmetic. We have developed here. We will not develop this arithmetic. But we give some examples of how one could work with this arithmetic. We have exercises where we will see some of the ways in which one can handle this arithmetic. (365) and 366. Okay, now let us briefly discuss what this means and what does proposition 36414 say. What it says is of course clear. Using this proposition in the way we are approaching, or we have developed everything up to this point, using this proposition we are relating the algebra of sets, where we have the set theoretic operations, to the arithmetic of the natural numbers. We already have natural numbers. However, instead of developing the natural numbers using the piano axioms, we can use these results as the basis for a definition of natural numbers and their operations. See, there is another way to define arithmetic operations on the natural numbers. According to that, what we will do is this: with every finite set, we will define a natural number. According to this approach, excuse me, I was bitten by a mosquito. Okay. According to this approach, definition of a finite set will be somewhat different. It can no longer be defined using natural numbers because we don't have natural numbers yet in this new approach. We will define finite sets differently, and with each finite set we will associate a quantity known as its cardinality, and those quantities will be called natural numbers. Okay, and those quantities of course would ultimately turn out to be the natural numbers that we have got from the piano axioms. But if one continues with that, one goes beyond finite sets, then one gets infinite cardinalities. Okay, those things are also there. For example, the set of natural numbers, we know that it is infinite. In fact, we have proved that. However, our definition of cardinality only considers finite sets. So this case is not covered. This itself, this set, however, has a cardinality associated with it, which is considered as an infinite cardinal number, which, if I am remembering it correctly, it's denoted by this symbol, Aleph naught. It's the smallest cardinality that is infinite. And when we will develop the system of real numbers, that will also be infinite. However, it has a cardinality which, although it's infinite, its size is, in a very well defined sense, bigger than the size cardinality of n. And that's what we said when in a recent remark we said that there are different sizes of infinity, that some sets can be more infinite than others. Now at this point I want to say something else. When set theory was developed by the famous German mathematician Cantor, he thought about a situation where this C denotes continuum, okay, the linear continuum of the real numbers. He thought that is it possible that we will have a set whose cardinality strictly lies between Aleph naught and C. He, for some reason, he felt that such a set cannot be there, that after Aleph naught the only larger cardinality is the cardinality of the continuum. However, he was not able to prove it or disprove it. The statement that there is no cardinality that strictly lies between these two is known as the continuum hypothesis. Cantor struggled to prove this hypothesis, or in some stages of his life he felt that it is wrong also, that there is actually a set for which the cardinality lies between these two. Now the thing is that afterwards mathematicians, or rather set theorists, logicians, were able to prove that this continuum hypothesis is actually outside of the, what can I say, it can neither be proved nor disproved using only the axioms of Zermelo-Fraenkel choice set theory. In that sense, it is independent of ZFC. Whether it is true or not cannot be decided from within ZFC, in the sense that using only the axioms of ZFC you can neither prove it nor disprove it. This peculiar situation shocked everyone, because people thought that whatever query we have about something in mathematics, that can either be proved or disproved. Yes, that is true. I mean, I should not say that is true. That question itself is meaningless unless we ask in what system we are considering that statement. We have ZFC and we are in fact studying it. It has its own universe, the observable universe of ZFC, which is defined to be those statements which can either be proved or disproved using only the axioms of ZFC. It is like our ordinary observable universe, the physical universe, the part of the universe which you can see, beyond which you cannot see, okay, because of finiteness of the speed of light. CH lies outside the observable universe of ZFC. Now, interestingly, very recently, I think 1 or 2 weeks ago, I have got a news that some logicians have come up with a new axiom which if you adjoin with ZFC, then one can prove that CH is false. That is, using that new axiom, one can construct a set whose cardinality lies between alpha naught and C. However, whether the new axiom is compatible with the other axioms of ZFC in the sense that they ultimately taken all of them together, we will not run into a contradiction. That I am not sure about that. Okay, so set theorists are doing research in these things, whether we can introduce a new axiom so that our observable universe expands, and whether CH or its negation can be taken inside of it. Okay, there are many interesting things in this part of, I should not say mathematics, but mathematical logic, where Kurt Gödel already proved that any formal system in which we have the arithmetic of these natural numbers, there will be at least one statement which I think he proved it cannot be proved, okay, using the axioms of that system. If I am stating it correctly, it cannot be proved or cannot be disproved, one of these two things, and Paul Cohen proved the other thing, that it cannot be proved or it cannot be disproved. You can search these things, you can look these things up, and you can see together their results show that within a formal system where we have axioms that are strong enough to describe arithmetic of natural numbers, there will be at least one statement which can be formulated using the tools of the system, but which one cannot decide whether it is true or not. To decide that, you have to add a new axiom, but then in the enlarged system, according to the theorem, again such a problematic statement will be there. So in this sense, mathematics is forever incomplete. No matter how many new axioms you introduce, at least one monster will be there which cannot be tamed. Okay, so I just wanted to say these things as a little digression. Okay, now here the text part of this section ends, and now we look at the exercises.